Okay, 1.1, power functions. Let's look at the definition of a polynomial function. The polynomial functions are functions that have the form a of n times x to the power of n. So some constant, some coefficient times x to raise to some exponent, plus successive terms that are very similar of another coefficient times x raised to another exponent, and so on and so on. So starting from the highest power of x, which we denote as n, the highest degree, then we can write, so x to the power of 5, then we write x to the power of 4, then the next term would be something x to the power of 3, and so on and so on and so on until you reach your constant term. So you have x at the end, and then your constant term. Now, you don't have to have every single degree represented, but generally this is what a polynomial function looks like. So n is the exponent, x is a variable, and a0, a1, an are real numbers, okay, and your coefficients. So for example, we have a couple of functions here. So here we have f of x equal to 7x cubed plus 4x squared minus 10x plus 3. So each term in this function has x raised to some exponent. At the very end, the x here is just x to the power of 0, but it's your constant term. Okay, so this is a polynomial, right? Notice that we do not have sinusoidal functions here. Notice that we don't have like sine of x. We don't have x as an exponent. We don't have x as a denominator. Okay, so this is a polynomial function. Okay, and remember, your exponents can't be negative either. It's only positive numbers here, whole numbers. G of x is another example. You can have coefficients that are negative or rational numbers as well. Okay, so here we're going to talk about what's leading coefficient. So when you look at the highest x term, x with the highest degree or highest power, for the f of x, we have x cubed. Okay, so it tells us that the degree of the function is 3. Okay, because the exponent 3, the cube, is the biggest exponent. Okay, the coefficient in front of that term, 7, would be your leading coefficient. All right, and for g of x, we have x to the power of 5, right? So that's the highest exponent. So the degree of the function is 5, and the coefficient in front of x to the power of 5 is -9, and so that's our leading coefficient. Let's look at some other vocabulary to get into to know. So the degree is a polynomial function is the highest exponent, okay, and it must be in standard form. So you would not be able to read the highest exponent in factored form unless you kind of did some work to make it look like standard form. Leading coefficient, we have, so that's degree. So leading coefficient is the coefficient in front of the greatest exponent of x. All right, so the leading coefficient determines the end behavior of a polynomial function, right? That helps us with that. So generally speaking, the sign, positive or negative leading coefficients, will tell us the end behavior. And so the end behavior of a function describes how the y values change, or where do the y values go as x approaches positive infinity or negative infinity, meaning as the graph moves to the left, where does y go? As the graph moves to the right, where does y go? So as an example, as the graph moves to the right, as x approaches a positive infinity, then maybe the graph will tend toward going to negative infinity. Or as x approaches infinity, we can write the word approaches, y is approaching negative infinity. Okay, so what does that look like visually? I like to show things visually. So if you have a xy plane, the graph could be going to negative infinity as x approaches a very large number. Okay. All right, let's look at even degree functions next. Okay, so even degree functions is the highest degree power in the polynomial is even. Okay, if a positive even degree function, let's look at an example of that. The leading coefficient is positive, okay, and a positive even degree function will start in quadrant 2 and end in quadrant 1, right? So quadrant 1 is here, quadrant 2 is here. Just to remind yourselves, 3 is down here and 4 is over here, okay? And so when you describe the end behavior of a positive even degree function, we look at what happens when we describe x going from negative infinity. So to the graph, as the graph goes further to the left, the y values become more and more positive, right? That's reflected up here in the graph. As the graph goes further to the right, the graph of f of x, the function, the y values approach positive infinity. Okay, so you get that from when you have an even degree function. So, power of 2, power of 4, power of 6, power of 8. We're talking about the highest degree power here. So the terms there could be other terms there too, but the highest term is up in even degree. And you have a positive leading coefficient. Okay. Now you can have a negative even degree function. So the leading coefficient is negative, and that starts at quadrant 3 and ends in quadrant 4. So as x goes to the left, negative infinity, y values go to negative infinity, or very large negative numbers. As x approaches very large positive numbers, the y values approach very large negative numbers. You can have odd degree functions. Okay, so odd degree when you have highest degree as power of 3, power of 5, power of 7. Okay, and if the coefficient is positive of that highest degree term, then your graph is going to look like this. It starts from quadrant 3 and ends in quadrant 1. And if it's a negative odd degree function, you could have a function that starts in quadrant 2 and ends in quadrant 4. Okay, so think of a graph like maybe you've seen this in grade 11, the graph of y equals x cubed. If you ever graphed y equals x cubed, right? There's an invisible 1 in front. Okay, it's a positive. So think about putting a negative x value into your function. Negative cubed is still going to be a very large negative number. So that's why when x goes to the left, you get very large negative numbers. And if you put in a positive number for x, then as x approaches large positive numbers, the function y values also approach very large positive numbers. Okay. All right, so those are some concepts there. So let's look at symmetry as well. We need to know symmetry. Even degree power functions have line symmetry on the y-axis, x equals 0. So all exponents must be even if you're going to have an even degree power function having symmetry about a line on the y-axis. Okay, and some odd degree power functions can have point symmetry about the origin. So meaning if I took this portion of my graph and rotated it, it will be symmetric about this point, the origin. Okay, and in this case, all exponents must be odd if that were to happen. So generally speaking, when we talk about even these kinds of functions that have symmetry, we call them even functions if they have symmetry about a line, the y-axis, and we call this one here on the right odd functions if they have symmetry about the origin. Okay, and we'll get to more that into in a bit when I do some examples. Interval notation. So let's talk about some interval notation you may have seen from before in grade 11. We talk about interval notation as a way to describe, say, a domain of a function. So there's some symbols we have to be familiar with. Open brackets, open parentheses means that the value is not included in the interval. So if I said 0 to 5, everything between 0 and 5, but I'm not including 0, I'm not including 5. Okay. Close parentheses means yes, I'm going to include the 0 now, and I'm going to include the 5. Okay. Infinity generally has a round bracket. We don't use a square bracket around that because infinity is just a representation of a very large number. It's not exactly itself a number. Okay, and then the union sign. If we're going to combine a couple of intervals, maybe from -2 to 0, combined with another interval from 1 to 3. Okay, so the union sign comes from kind of set theory in logic, mathematics. Might be so we bring that here. Union meaning we're going to combine these two intervals. Okay. All right, so let's look at some lesson examples for this section. So fill in the missing spaces in the following table to practice the different notations. So let's look at the notation. So you may have, so this is not, you may be familiar with set notation. Here's another form of notation. The interval from -3 less than or equal to x less than or equal to 5. So we're including -3 and we're including 5. On a number line, that could look something like this. So I could put -3 on the left, 5 on the right, and let's use a thicker. There we go. There it is. Make that those 2 points bigger. There we go. So that would be a representation of -3 to 5 on a number line. Solid dots on -3 and 5 to indicate that we are including those points. In interval notation, it'd be written like this. We're going to use square brackets, -3 and 5. Okay. What about the next one? X is less than 2. So x is less than 2 means we're going to have 2 on our number line, and we're going to put a point there. Oh, well, it's less than not equal to. Okay, so it's going to be a rounded point, and every number less than 2 means I have to kind of cover the rest of the line like that. Okay, and so if I'm going to write this in interval notation, it's going to look something like this. We're going to go from -infinity. Oh, let me change to, okay, -infinity all the way to 2, and we're not including 2, so it's going to be a round bracket. Okay, what about 3 to 8? We're not including 3, but we are including 8 because of the less than or equal to sign. So if we're not including 3, okay, so we're going to put a round circle there, and let's put 8 over here somewhere. We're going to make that a solid circle there. There's 8, and then I'm going to just draw the interval. Okay, x is greater than -3. We can have representation of that. So -3. We're not including -3, but we're including every x value after it. Okay. Oh, I forgot to write the interval notation. So for x, for 3 less than x less than or equal to 8, that'll be written like this. So round bracket for the 3, but a square bracket for the 8 because we are including the 8. And for the next one, -3 and anything above it will be a round bracket on the -3 and then infinity for the next part. So it's always interval notation, start with the left number on the first number and then the right number on the right. And if it's an open-ended interval, you're going to be using an infinity sign. Okay, what if you have a combination, such as the next one, from -1 to 5? All right, so let's put -1. It's going to be a round open dot because it's not including -1, but we are including 5. So it's going to be a solid dot for 5. And then we're going to look at the interval from 6 onwards. So let's make it scaled right here. So 6 will come right after 5. And when I connect them, I'm going to connect them like this. So from -1 to 5, you're not connecting 5 to 6. It's not included in the interval here, but from everything 6 onwards, it is. Okay. And so if I write that in interval notation, we're going to need to use our union sign. So we're going to say -1 to 5 square bracket in union with square bracket 6 all the way to every other number afterwards. So infinity. And infinity always has round brackets. What if you're talking about every real number? Every real number will have an interval of -infinity to infinity. Okay. What if x is not equal to 1? Well, then we're going to just put a 1, a round hole, not including 1, but we're including every other x value. For this one is okay. And if we're including every other x value, then in interval notation, it would look something like this, right? -infinity to -1 round bracket, because we're not including 1, in union with -1 to infinity. So we're just not including -1, no square bracket there. And for x less than or equal to 0 and x greater than 2, well, we put a solid point for 0 and include everything below 0. There, I draw my purple line there. And for 2, so we'll go to 2 round, make it an open hole there because we're not including 2, and everything after that is included. And so when I write my interval, we shall say -infinity to 0, square bracket, because we are including the 0, in union with round bracket 2 all the way to infinity, and a round bracket around that. Okay. Let's look at some other polynomials here. State the degree and leading coefficient of each polynomial. So when you look at the term with the highest degree, it may not necessarily be the first term, right? If you look carefully, if I rearrange this in order of degree, I'd write 2x to the power of 6 first, minus 5x cubed minus x plus 1. And that will kind of show to you that, hey, this is the highest term, the term with the highest exponent, I should say. So my leading coefficient would be here, 6. So leading coefficient equals 6. And the, 2, the coefficient in front of that is 2. And the degree is 6, okay? And then looking at the next one, as I said, if you're going to determine the degree and leading coefficient of a function, you have to have it in standard form, right? So if I were to look at the next question, I might have to expand this one. So I'd say here 2 minus x, x plus 1 squared would be x squared plus 2x plus 1. And if I expand this even further, I'll have 2x squared plus 4x plus 2 minus x cubed minus 2x squared minus x. And I could, I'll just complete it by simplifying everything, collecting like terms minus x cubed plus 3x plus 2. Now, and this would tell me, hey, look, if I finish expanding this, I have this in standard form. X cubed is my term with the highest exponent, so degree is 3. The leading coefficient is, well, there's a negative there, also a -1. Okay. Now you don't have to go through all the work expanding this if you just recognize, hey, if I look at this term, x plus 1 squared, this x is going to multiply by itself to give me x squared. And then that x squared gets multiplied with this minus x over here. And if there were any coefficients, you'd multiply those coefficients together as well. And then you could realize, hey, you know what? I'm going to get a minus x cubed at the end anyways. So you could multiply all the x's out until you get an x cubed. And you can also see that by looking at, hey, you know, this factor is a linear factor. And then this factor here is a quadratic factor. So a quadratic times another linear, x squared times x gives you x cubed. So there are a couple of ways you can take shortcuts to get the quick answer. Looking at the third example, h of t equals 10. This is just a constant, right? But this is also a polynomial because it's just like saying 10 times x to the power of 0. And if you recall your exponent rules, anything raised to the power of 0 is always going to be 1. So saying this is a constant tells us that here my degree is 0. Okay, it's still considered a polynomial. And the leading coefficient is equal to 10. Okay, let's continue. Next example. For each function, state the domain and range. Describe the end behaviors. Identify any symmetry. Okay, so let's look at this function, y equals x to the power of 8. Okay, something big. Well, let's just kind of remember, hey, you know, we're all familiar with y equals x squared from grade 10, right? Quadratic function. What do you know about that parabola, right? Just parabola. Okay, that's in quadrant 2, as x approaches negative infinity, y values are approaching positive infinity. And in quadrant 1, as x approaches positive infinity, y values approach positive infinity. X to the power of 8, it's just very much the same thing. It's just a much more faster growing graph, right? It's going to have both ends of its graph going to positive infinity. So when I look at domain and range, let's say my domain is going to be, well, every x value counts. I don't see any way there's no x values that don't count here. So I can put in any x value for x to the power of 8 and it'll work. And for my range, well, just like x squared is, 0 is going to be my lowest value, and that should be a square bracket. Right? So if I put x equals 0, y is also going to be equal to 0. And it's going to go approach positive y values everywhere else. So it can go potentially up to infinity there, very large y values. So there's my range. Describing the end behaviors. So then we can say here, hey, if I put as x approaches very large negative values, then y will approach very large positive y values. So negative infinity, and y tends to positive infinity. And then as x tends to very large positive values, infinity, then y will also tend to approach very large positive values. And I'll write infinity for that as well. Okay. So nowhere can we ever get a negative number, right? So 8 is an even number. So multiplying a negative number 8 times, well, that's always going to yield, or an even number of times will always yield you a positive number. And for part 3, identify any symmetry. Well, this is the kind of graph that's going to have a symmetry, line symmetry at x equals 0. Right, so this is, remember, this is x equals 0. It's going to have line symmetry. So whatever you see here on the right side will mirror itself on the left side about x equals 0. So this is a graph where every term is even degree. There's only one term, but it is even degree. The leading coefficient is positive, so therefore it is a even symmetry. It is symmetrical about the line. So it's an even function. And so we have line symmetry about x equals 0. Okay. Let's look at the next function. G of x equals negative 3 times x to the power of 5. All right. We now have a leading coefficient. Let's talk about domain and range. So we have well, okay. Think about functions we know of that have an odd degree, right? We know a line, right? We know x to the power of 1. That's an odd number. One is an odd number. If it was a negative leading coefficient, yeah, there would be a line that slopes downwards. So very similar here, negative 3x to the power of 5. You have a leading coefficient that's negative, and a degree is odd. Okay. So it's going to have to follow the same kind of reasoning as negative x. The graph of y equals negative x. Right? This is the graph of y equals negative x. It has to have that kind of end behavior, right? So it's going to start up here in quadrant 2 and end here in quadrant 4. Okay. So what does it say about our domain and range then? So of our domain, well, it looks like I can put in any x value here, any x value. Generally for polynomials, unless there's an application problem where you do have some restrictions, the domain is every x value. Okay. And then the range will be every y value, so negative infinity to positive infinity. That's how I'll write. This is how I write it. For negative infinity using interval notation. Negative infinity, comma, positive infinity. Okay, and then the end values. So then our end behavior, as x approaches negative infinity, or very large x values, and y is going to approach very large positive y values. Y approaches infinity. And then as x approaches very large x values, positive x values, y will approach very large negative y values. And y tends to negative infinity. Okay, so that's how we can write that end behavior statement. What about symmetry? Well, because every term in this is odd, and there's only one term. It's just one term, but the degree is an odd number, and that's the case. Remember what I said? Let's look back up here in my notes. Always refer to your notes, right? So odd degree power functions have point symmetry around the origin. All exponents must be odd, and it is, right? So odd, I only have one term, so all that's fine. So one term, it's odd, so it'll be symmetric about the origin. Okay, so therefore, odd function symmetric about the origin. All right, let's get one more. Well, f of x equals negative 2 over 3 x to the power 4 here. The leading coefficient is negative 2/3. Negative, okay, it's negative. The degree is 4. It's an even number. Okay, so what does that tell us? Well, think of the negative number as like a reflection in the x-axis, right? When you're doing transformations. So your parabola now like looks upside down. So it's going to start in quadrant 3, okay, and then in quadrant 4. All right. So what does that say about domain and range? Number 1, domain. Every x is valid, so negative infinity to infinity in my interval notation. My range, well, it'll go from 0, and it's going to be a square bracket because 0 is included. If x is 0, then y is 0. And it will go down to negative infinity, very large negative numbers. There are no positive numbers here because of that leading coefficient. So my end behaviors is going to be described as follows. As x tends to very large negative numbers, y will tend to go to very large negative numbers. And same thing for as x approaches positive infinity, y will tend to negative infinity. Okay, and then is there symmetry? Yeah, there is line symmetry. Remember, this is an even exponent. Every term is an even degree, even though there's only one term, that's okay. And so we have line symmetry. Okay, let's look at some graphs. So in this course, we are looking at graphing and properties of graphs. So consider each graph. Number 1, state the sign of the leading coefficient, justify your answer. State the domain and range, state any symmetry possible, and describe end behaviors. Okay, so just looking at this graph, I'm going to introduce to you something about turning points here. You have like a little turning point up here and a turning point down here. Think of them as, these are local maximums and local minimums. Okay, and if you see something like this, that can give you an indication about what kind of function this is, right? Let's talk about what functions that we do know, right? So if we have a linear function, there are no turning points, right? So this is a degree 1, 0 turning points. Think of next a parabola, degree 2, we have 1 turning point. Okay. And now what happens if we have a degree 3 function? We could have degree 3 and 2 possible turning points. Not all the time, you're not going to get, because, same, it's not going to, it may not be always turning points. You could actually have none. But look at the pattern, right? Degree 1, 0. Degree 2, 1 turning point. Degree 3, 2 turning points. Okay. So the degree of the function, or the number of turning points, is an indication of the degree of the function, or at least the least degree, right? So this, at least, without seeing the rest of the graph, we can say at least this function has to be degree 3 if we're describing this function as a polynomial. Okay. Okay, so if that's the case, so we're trying to convince ourselves this is of a degree 3, and so this is an odd number, right? Odd number. Okay, so what do you know about an odd degree function? Well, they could have a positive leading coefficient, like a positive y equals x, right? So they start at quadrant 3 and go to quadrant 1, or they could have a negative leading coefficient, like y equals negative x, starting at quadrant 2 and ending in quadrant 4. Well, here we start in quadrant 2 and we're ending at quadrant 4. So that tells us our leading coefficient is negative. We don't know what the number is, but we know it's negative. And that's the point of the first question. State the sign of the leading coefficient. Okay. Domain and range. Okay, so that was part one. Part two, domain and range. We're going to look at negative infinity to infinity every x value. And for our range, it looks like it goes from negative infinity to infinity as well. Okay. State any symmetry if possible. Well, because we're dealing with an odd degree function, there is no line symmetry, but we could potentially have point symmetry. But in this case, we don't, because the condition for point symmetry, well, you have to be symmetrical about the origin. And so here is the origin, and we can clearly see the graph does not pass the origin. So no point symmetry. Okay. And then if I describe the end behaviors, just as we've been doing before, the end behavior for a function like this, as x tends to negative infinity, y tends to positive infinity. And as x approaches very large positive values, y will approach very large negative values. Okay. So that's how you can analyze the graph using some of these concepts we're learning in this particular chapter section. Looking at the next graph, okay, again, the assumption here is we're working with polynomials. Okay, if I see a polynomial here that is how many turning points? 1, 2, 3 turning points now. Then let's consider that the degree now is of degree 4, right? If you look, okay, so if degree 3 is that 2 turns, something with 3 turns would be degree 4. So the number of turns is always 1 less than degree of the polynomial. Okay, so minimum degree 4. Okay, so let's say that degree 4. Okay, because of 3 turns. And so degree 4, it's an even degree. Think of your parabola. If we're starting in quadrant 3 and going to quadrant 4, so your leading coefficient then is going to be negative, right? So leading coefficient is negative, right? It's like think of your base parabola, positive leading coefficient, y equals x squared, 1x squared, both point up. But the moment you reflect that parabola down below, okay, y equals negative x squared. Okay, now we're just, instead of saying x squared, we're saying x to the power 4, x to the power 4. Okay, leading coefficient is negative. Domain and range. Domain, every x value is going to work in here. The range, however, is going to be restricted here. We are only dealing with negative y values all the way up to 0, including 0. Okay. Now it looks like there is a horizontal shift. So like this point might have been shifted this way. There's no line symmetry. We're specifically looking at to see if there's any line symmetry about x equals 0, and I don't see it. So no symmetry. Okay, and the end behavior as x approaches very large negative numbers, negative infinity, then y tends to negative infinity. And as x approaches positive infinity, y tends to negative infinity. So both are going to tend to, y tends to negative infinity. Okay, let's look at another one. Why don't I pause the video, or why don't you pause the video and try this yourself, see what you can do. Okay, so hopefully you got a chance to try that. 2 turns, so the least possible degree is 3. Okay, no symmetry, even though it passes through the origin, it doesn't look like this is going to be symmetrical. If I rotated this portion of the graph, it won't look the same. Okay, and need a negative leading coefficient. If we start from quadrant 2 going to quadrant 4, that's a negative leading coefficient, and there's my end behaviors. Okay, let's move on to, this part of the lesson. Homework listed questions here from the textbook. So by no means are these the only problems you should try. You should try to attempt more, but at least at the bare minimum, try looking at these ones to get a good understanding of the concepts here. Okay, that's it. See you in the next video.